In business, it is just as important to know when a plan might fail as to know when it will succeed. Since many businesses are modeled using mathematical equations, we can use theories of math to help determine when an equation's derivative may fail to exist. Hi, my name is Jason Rosenberry, and that is what we will be discussing in today's lesson. Let's start by establishing when a derivative may fail to exist. A function will not have a derivative at a point P located at a f of a where the slopes of the secant lines, which is f of x minus f of a over x minus a, fails to approach a limit. Some examples of this are 1. A corner, where the one-sided derivatives differ, as in the function f of x equals absolute value of x. Let's sketch that graph. Looks something like this. So as you can see, we have a corner at x equals 0. So at x equals 0, the derivative would not exist. 2. A cusp, where the slopes of the secant lines approach negative infinity from one side and positive infinity from the other side, as in the function f of x equals x to the 2/3 power. And let's go ahead and sketch what that graph looks like. Cusp looks something like this. So again, at x equals 0, the derivative of f of x equals x to the 2/3 would not exist. 3. A vertical tangent, where the slopes of the secant lines approach negative infinity or positive infinity from both sides, as in f of x equals cube root of x. F of x equals cube root of x looks something like this. So at x equals 0, you can see we have a vertical tangent line. So at x equals 0, the derivative would not exist. And 4, a discontinuity, where one of the one-sided derivatives is non-existent. An example might be the unit step function. Let me sketch that graph. Something that might look like this, where we have a complete discontinuity at x equals 0. So there again, the derivative would not exist at x equals 0. Let's try an example. The function shown below fails to be differentiable at x equals 0. Tell whether the problem is a corner, a cusp, a vertical tangent, or a discontinuity. Since we want to differentiate at x equals 0, and we know that at x equals 0, y is equal to 1, but for the inverse tangent function at x equals 0, we would get a value of 0, not 1. So this problem is a discontinuity. A good way to think of a differentiable function is that they are locally linear. That is, a function that is differentiable closely resembles its own tangent line close to the point A. Let's try this idea out. Let's take a look at the function f of x equals x times cosine 3x. And let's take a look at what's happening at the point 2, 1.9. So over here on the left-hand side, here is f of x equals x times cosine 3x, and we're going to zero in on the point 2, 1.9, which is right about here. And what we're going to do is slowly zoom in at that point. So the next graph that you see here, let's compare this graph with the first graph. Again, we're zooming in at 2, 1.9, which is right about here. And now start looking at the curvature of the graph. It's becoming less curved. So again, keep on zooming in, and here we are again at that same point, zoomed way in. And as you can see, the curvature is starting to go away. So the closer we get to that point, the graph is appearing to be a straight line, or appearing to be what is known as locally linear. Locally linear applies that when you get close to zero, or I'm sorry, zero in on a specific point, you can see that it's approaching a straight line. Some graphing utilities can approximate a derivative numerically with good accuracy at most points of their domain. Let's see how we might do this. What our calculator will use is a symmetric difference quotient f of a plus h minus f of a minus h all over 2h, using a very small value for h, which is similar to taking the limit as h goes to 0. This is all done in the function NDER, which takes three arguments: the function, the variable, and the value at which we wish to approximate the derivative. For example, let's compute the numerical derivative for the function x cubed with respect to x at the value x equals 2. So what we're finding again is the numerical derivative of x cubed at x equals 2. Here are the steps you would perform in your graphing calculator. Select the Math button, choose option number 8, which is numerical derivative. Now we type in the function, variable button raised to the third power, comma with respect to x, so comma variable button, comma at x equals 2, and close the parentheses. So what we're seeing here is that the numerical derivative is very, very close to 12. We can also use this to graph the derivative of a function. Use the numerical derivative function of your calculator to graph the derivative of the function. If possible, identify the derivative function by looking at the graph. So here we have y equals x times the absolute value of x over 2. We're going to now have the calculator graph the derivative of this function. On the calculator, perform the following key punches: y equals math 8, left parenthesis, variable button, times, math button, right arrow, number 1, variable button, right parenthesis, divide by 2, right parenthesis, comma, variable button, comma, variable button, close parenthesis, and graph. What this will do is yield the following graph. This is the graph of the derivative of that previous function, y equals x times absolute value of x over 2. So do you recognize this graph? Sure, this is the absolute value graph. So earlier we had y, if y is equal to x times absolute value of x over 2, we see that the derivative is absolute value of x. Let's move on to look at a theorem that connects differentiability to continuity. Theorem 1. Differentiability implies continuity. If f has a derivative at x equals a, then f is continuous at x equals a. Note that this theorem says that if a function has a derivative, then it is continuous, not the other way around. And this idea leads to another. Theorem 2, the intermediate value theorem for derivatives. If a and b are any 2 points in an interval on which f is differentiable, then f prime, or the derivative of f, takes on every value between f prime of a and f prime of b. Let's try an example that will help illustrate the conditions that are necessary for the theorem. Here's our example. Does any function have the unit step function as its derivative? That answer is no. Choose any a value that's negative. Choose any a value over here that's negative. We see that the unit function tells us the unit function evaluated at a, where a is negative, we get -1. Now choose any b value that's positive, something over here, and we see that the unit function evaluated at b gives us +1. Notice that this function does not give us any value in between -1 and +1. Now it's time for you to try a problem. Show that the function given below is not the derivative of any function on the interval, the closed interval, from -1 to 1. f of x is equal to 0 when x is between -1 and 0, including -1 and 0. f of x is equal to 1 when x is between 0 and 1, including +1. Pause the video while you work on this problem. When you are finished, restart the video to check your solution. So in the interval from -1 to 0, including -1 and including 0, choose some value for a. So choose a in the interval -1 to 0. In the other interval from 0 to 1, including 1, choose some b value. So let's choose some b value in the interval 0 to 1. So we see that f of a would equal 0, f of b would equal 1. So function f, does not take on any value between 0 and 1. So the function f of x does not have the intermediate value theorem. In this lesson, we explored why a derivative may fail to exist and the intermediate value theorem for derivatives. Be sure to work the exercises that your teacher assigns. We'll see you next time.